So I prepared a little bit. I'm going to talk about how to obtain smoothings. And there are two steps. Andrea, in his first lecture this morning, very nicely, he made an overview of the different problems that you may have with Fanos. And there's an affine situation where you want to have a smoothing. And there's also a compact situation where you want to have a smoothing. Both of them are a challenge. So I start in my first part, maybe half of my talk, it's going to be the affine case. And the second half is going to be the projective case. All right. So in the affine case, so that's about proving the CFP conjecture. CFP is Corti-Filip-Petracci. You see here the conjecture sketch more or less that we already saw this morning in Andreas' talk. You start with an affine Gorenstein toric variety X, and then the conjecture is a bijection, a statement about the existence of a bijection between the classes of zero mutable Laurent polynomials attached to the polytope that gives the affine variety, and then that matches with smoothing components in the versal deformation space of X. Okay, so far that's entirely conjectural. And now like to have an extra part here that was already indicated by Andrea in the morning, namely an auxiliary bijection here that identifies the left-hand side with the set of log structures, okay? Singular log structures on the Mumford degeneration of X. Okay, so there was a question this morning, is the space that we put a log structure on reducible? Yes, it is. That's when log structures have something to do. They are most powerful when you have a reducible space. So we make the affine variety that we want to smooth. We artificially make it reducible by degenerating into separate pieces. There's this concept of a Mumford degeneration. That does it, Andrea already talked about in the morning. So we degenerate it. That's a straightforward process. It's canonical. And then you want to put a log structure on it. And that process of putting a log structure on is not canonical, but the choice of log structure is in bijection with the left-hand side here, which is the class of zero mutable Laurent polynomials. And then you're good enough if you make sort of a bijection between the bottom thing and then the right-hand side, which are the smoothing components. And so what we're going to prove in this talk is that there exists a map here, okay? A map. And, you know, in order to know that it's a bijection, it's extra work that we might be able to do in the future or not. But let me just focus on that now. So we have put a single log structure on the Mumford degeneration. So it's an affine variety, X is affine, but it's not reducible. And then we want to produce a smoothing of X. Now I'm using X in two ways. I'm using it as the original one, and then it's affine degeneration. From now on, it's going to be only the affine degeneration. I'm mixing them, so sorry for that. It's going to have to use notation, but I don't want to put another variable here. So X now is a reducible one. It's a degeneration. So you first degenerate, then you smooth it, and it's going to be the smoothing of the original one, you know, if you were lucky. So that's another step we need to show. Okay, so there's an assumption that we use in order to construct such smoothing. And the assumption is the following. I mentioned this in the morning already. Assume that the singular log structure that we put on X by means of this bijection permits a log smooth resolution, that there exists a log smooth resolution. So we call that X tilde, and we map down pi. And I gave you this baby example in the morning where you could see what it might look like, this log smooth resolution. And the example I gave actually is a generic situation, always happens in codimension 1 laws, looks like that. Yeah. So once again, X now is the bottom thing here is affine. That one's affine, but it's reducible, has a single log structure. And then we blow it up in some way. And So the one point of this assumption is that it's kind of a remark that it exists. Okay, so the remark is these three solutions. So it's log smooth and log rapid. I didn't say that. These solutions are expected to exist. In all these cases then when needed, okay, whenever needed. And if you want to know why, then the host is the person to ask. So I put here Alessio. So all the questions on that point go to Alessio, all right? So that's the assumption. We assume we have a log smooth resolution locally. The goal is then produce a smoothing of X. Produce a smoothing. Okay, that's the goal. Step one for that is to compactify the situation. So that means we have the original log smooth resolution. We compactify by a normal crossing divisor to X bar. So the divisor is as an AD, and then we do the same on the resolution. So there's a divisor here as well, compatibly. Okay, that makes the situation compact, and that's necessary. If you like, you can also have a projective. You don't really need that, I think. But we compactify, okay. So once you have this compactification, we can actually obtain a smoothing upstairs of this resolution. Okay, so how does that work? Remember from my talk in the morning, I gave you a theorem that was proved jointly with Felten and Philip. And we can simply apply that. So since this upstairs space is log smooth, and it's log Calabi-Yau by the discrepancy, and log Calabi-Yau, we can apply the theorem from this morning, can apply smoothing. So it was Philip-Felten theorem to have the smoothing, okay? The smoothing. So that's pretty simple, huh? So you just use that theorem, and then that's pretty much it. So the original space, smoothing means original space is the zero fiber. You have a holomorphic disk, and then you have a total space of the deformation. You embed that central fiber in the deformation. The nearby fibers, when the base point is non-zero, they are smooth. That's what it is. So this thing does exist. You know, it's readily being produced by the theorem. Then the next step is to turn it down, to bring it down, push it down. So we're after a smoothing of X, and that can be achieved as follows. You can take global sections. Okay.
Are you carrying the divisor with you?
Yes. Yes, this divisor D is an important information. It's a vertical divisor in terms of this deformation, and it's carried with it. So I know it also in the nearby fiber exists there as well. Very important point. Having that allows me to go back to the affine situation, so basically to unprojectify. So what I can do is, oh yeah, maybe I should say that there's this divisor, as Miles pointed out. It's like a family of divisors, one of each fiber, and I can then go to the complement of the divisor. Okay, so look at the smoothing space minus the divisor. And so that has a structure sheaf. Okay, take global sections of the structure sheaf of that. Let's do O. Okay, structure sheaf. Taking global sections of that. That's meaning pushing down the deformation. Okay. Global sections of the sheaf, and that produces a deformation downstairs. Produces deformation. And then you need to check is it smoothing. That's going to be fine. Okay. Deformation downstairs. Check it's smoothing. All right. So that was a quick thing. We're done now. We can go home. Except maybe you want to know uniqueness. Okay, how is it well defined? So remember that I actually wanted to construct a map here, right? So I'm given a single log structure, then I have a resolution, but that might be a choice. You can have different resolutions. And I've now used the resolution to produce a smoothing of X downstairs. But how about if I use a different resolution to get the same smoothing? Okay, so that's a question. Or even, in fact, with the same resolution, you know, I can study, is there different smoothings, or are they unique in some sense? And we'll find some uniqueness properties indeed. Okay, so question about uniqueness. So in the morning, I talked about the log conifold. For instance, log conifold does have different deformations. It has a smoothing deformation and non-smoothing. So, you know, there might be similar things happening here too. In order to get to the question of uniqueness, that's, you know, usually classified by looking at the derivation sheaf and then looking at H1 of that. We're going to get to that, and ideally that's going to be vanishing, some kind of vanishing statement. Here's a way to study that. Okay, we'll take me the entire right column here to explain that. We compare the log-Hodge-to-Durand spectral sequence upstairs and downstairs. We work with the compactification once more, you know, because the thing is compact, these spectral sequences are nice now, vector space are finite dimensional. So the log-Hodge-to-Durand spectral sequence upstairs, at E1 it looks like this. You have this space upstairs, and then you take the differential forms upstairs. I denote them W. You can also use omega upstairs, it's log smooth there. But I allow log poles also in the compactifying divisor, okay? That's what I usually do, we work with compactifications. And then that has an abutment to, you know, the hypercommodity of the complex, but I don't write it down. And I have the same sequence downstairs, E1, that's just very similar. So here, instead I use the compactification downstairs. And here, W, remember, is the thing that's being pushed forward from the log smooth locus. Downstairs I have log singularities, and I'm considering differential forms, log differential forms that are being pushed forward from the log singular locus, log smooth locus. Okay, that's why I call it W, not omega, as you usually call it. And there's a map now, it's just a pullback map from the sequence in the bottom to the sequence at the top. And the question is, what does this map do? Okay, so that's some information about this map. So first of all, there's four observations. First is the spectral sequence upstairs. Degenerates at E1, okay, because the situation is log smooth. Degenerates at E1. That's very nice. That's by work on log smooth stuff by Giluzzi, Cutler, and so on. By log smoothness. So that's Cutler, Giluzzi, others. That's the first point. Now the next point is some relationship. How about this map, the pullback map, okay? So the map, I claim, is injective. How do you prove this? Use for that Grothendieck duality. It's an argument I learned from Steenbrink in his work, vanishing homology and V manifolds and so on. Grothendieck duality. In order to use Grothendieck duality, you need to identify the dualizing sheaf. And there's a very nice statement to know what the dualizing sheaf is. Namely, in these cases, these are, you take the differential forms, you take the top degree, the dimension, and then you adjoin the negative on the boundary divisor. Okay, so this is the dualizing sheaf. Is dualizing sheaf upstairs, and that's by work of Tsuji. Okay, so reference here to Tsuji. So he worked in locksmooth setting. He identified the dualizing sheaf. Very nice. And the same is downstairs. You have the sheaf, same statement, minus d. Okay, and then there's a map between them. And the nice thing that's on the top cohomology, that's an isomorphism. Okay, dualizing downstairs. And now that information is enough, and information that you can pair forms. Okay, so there's a usual Serre pairing, or it's generalized to Corti-Felten pairing. You have information that the dualizing sheaves are compatible and produce an isomorphism. That's enough to know the injectivity of the lambda vector sequences. Once you have that, you conclude readily that the spectral sequence downstairs also degenerates. Because if you have an injective map on E1 and map of spectral sequences, upstairs degenerates, also the downstairs degenerates. Spectral sequence downstairs degenerates also. Nice, okay. Finally, I want even more. I want that the map pi star is actually an isomorphism.
Oh yeah, so how do you know that pi star is an isomorphism? Both sequences abut to the usual cohomology of the Kato-Nakayama space. So remember in the morning I told you about the Kato-Nakayama space, and we studied it in the baby example and said that in the resolutions we're looking at, log-smooth resolutions, they induce a homotopy equivalence on the Kato-Nakayama space. In particular, you have an isomorphism of the ordinary cohomology of the Kato-Nakayama space. Now, because both spectral sequences abut to exactly that cohomology of the Kato-Nakayama space, which is a topological model for the nearby fiber in a smoothing, if you had a smoothing, because it's an isomorphism on the abutment, you find that it's actually an isomorphism. So that gives you an isomorphism. Thus, to be completely honest with you, it's not proved yet that the sequence downstairs abuts to that Kato-Nakayama space also, but I'm sort of confident I can prove it. One needs to extend some work of Ogres to get it done, but I think it's just a technical thing. Okay, so once you have that, you get this. That is isomorphism. All right, now that's nice because we know that the situation downstairs is so that the space is affine, right? So because X is affine. Oh, sorry, no, we have still compactified. All right. Yeah, no, sorry. That's the next step. I've gone ahead of myself. I'm going to the next step here on the next page. Decompactify. Okay. So once we decompactify, you use affineness. To decompactify, I consider a Czech cover. Consider a Czech cover consisting of 3 open sets, and I use 2 covers, one upstairs and one downstairs. So upstairs, I'm using the open pieces, the affine part, so that's before compactification with this affine part, and downstairs I use that as well. And then I use the complement of the locus that gets resolved. So there's the log singular locus downstairs and upstairs, and I'm removing that so that on the complement I do actually have an isomorphism, right? Remember, that's a resolution, so on the complement of the stuff that's bad, it's just an isomorphism. And then to finally
Sorry,
cover
just
everything, you still also need a neighborhood of
Helge,
what's
just
left,
interrupt.
which is the boundary divisor intersected with the bad locus, the exceptional locus. And downstairs, it's just a neighborhood of the log single locus.
Can you hear
As
me?
the boundary divisor. Okay. So and now the cover, yeah, consists
Helge,
of
you're
three open
having a
sets.
question and you're ignoring it.
Sorry.
What's happening? Can
No, can you hear me?
Can you hear Andrea?
Yeah, I can hear you.
So I have just a stupid question. This is not an affine cover, or is it?
Okay. Can you say again?
Is it an affine cover?
Yes. Wait. No, it's not. No, sorry. It's not affine. I don't expect it to be affine. Yeah. So I hope that's not a problem. Yeah, I mean, you can do check cover with non-affine things. So the individual pieces may have cohomology. Work with possibility of cohomology. I use this check cover. So eventually I'm after knowing what happens on the affine patch. That is the non-compactified part. And the cover is such that I always have maps from the pieces one to the other. So the cover is compatible upstairs and downstairs. So in the Čech complex, I get a map of Čech complexes. But the Čech complex may have the terms, and Čech complex may have higher cohomology. If you want, you can resolve sheets and then you have a double complex. Okay, so the point is now you get a map of Čech complexes. For the sheaf WP. And we know from the previous step this is an isomorphism on cohomology. Right, so in the previous step, we know the Čech cover computes the cohomology of these groups. We have them in the previous page in step 3. We know that the map pi star is an isomorphism on those cohomology groups. Hence, in the whatever the Čech complex computes its cohomology in these groups, it's an isomorphism. So yeah, the cohomology on the cohomology of the Čech complex, we have that this is an isomorphism. And the funny thing is now we want to deduce from knowing that it's an isomorphism on cohomology that it is an isomorphism also on terms. Okay, it's a funny concept. At least I find it funny. But the thing works. So you deduce from the isomorphism on cohomology that you have an isomorphism on terms. And this goes as follows. If you look at what happens, so the middle thing is right on the nose in isomorphism, because these are isomorphic varieties. And then something happens on the left and on the right. And of course, you've also intersections of these open sets, right? So on the left-hand part, you can treat by induction. Okay, if you prove that something works in lower dimension, because the left-hand side, the bad locus is stratified, so you can treat the right-hand side by induction by dimension. And then the only thing where really something changes is the left-hand side map. And because there's only one term where really something is different in the complex upstairs and downstairs, because in isomorphism cohomology, it has to be an isomorphism with one term, otherwise it would not be isomorphism cohomology, right? So that's funny. I summarize by induction on dimension. We get the following. So comparing complexes, we get that the first term cohomology agree. Okay, so this x tilde p, that's the cohomology upstairs, and it has to be isomorphism downstairs. Otherwise, the Czech complexes couldn't have isomorphic homologies, which we already know. Okay, so then I call this step decompactify. We know the isomorphism of a compactified version, and we deduce from that version the isomorphism of the non-compactified. Okay, and now the cool thing is that the right-hand side here is affine. This is affine, so it doesn't have higher homology. So we've deduced from this quite a powerful statement, namely that the higher derived images of the log Durand differentials are 0 for q greater 0, and that also the 0 degree has the property, it's also super useful, that if you push down the piece differentials on the resolution, you do get the differential downstairs. Also very useful. Okay, that's the q equals 0 part. So very nice. And a direct consequence of that, in particular, using crapancy. So the resolution is crapant. Upstairs, the thing is Calabi-Yau. We have that the first homology of theta. So the log derivations, this vanishes because that's just isomorphic to to w dimension -1. Yeah. Okay, so that's one of these things. I've just shown that the higher homology vanishes, and that's the rigidity statement that I was after, saying that upstairs there are unique log deformations. Okay, so the smoothing that we constructed with the theorem, that was just a very quick shot at the beginning of the talk, the smoothing is actually unique by the statement because we just proved the rigidity of it. Okay, so that means that we have a unique smoothing upstairs. Nice. Next step. We want also a unique smoothing downstairs, all right? Upstairs unique, but we can still choose a different resolution. And we want independence of the choice of resolution. You know, imagine you have two different resolutions, both give you smoothings downstairs. Why would they agree? Okay, so that's also quite a lengthy proof here, but we can just adapt something that has been done before by people. Obviously, independence of the chosen resolution, or equivalently, and the uniqueness of the deformation of the smoothing downstairs. Smoothing downstairs. So that's of x, okay? So this works by adapting. Similar proof by Gross and Siebert. So Mark and Van proved something in a similar situation. It's a different setup, but proof can be adapted. Okay? And the proof that we use really crucially uses once more that there's rigidity upstairs. Okay, so this is a crucial ingredient. The rigidity upstairs then allows proof rigidity downstairs. Okay, nice. So here with that we finished constructing the map. Let's go back here. So we actually achieved, I gave you this map now. Let's wait until the screen updates. Other questions to this construction? Okay, so I showed you that there's a unique way to obtain the smoothing for the space downstairs. The smoothing is unique, so there's a natural map. Of course, you want to know that it's bijective, okay, to actually fully prove the conjecture. You want to know it's bijective. You know, that would be a different talk about it. Maybe not actually my work on those. Okay, no questions. Then I would go to the projective case. That's part 2 of my talk. the global case, smoothing projective Fano varieties. Okay, so what I do now is want to use the previous situation as a local model for a global case. Imagine we have a toric Fano variety, projective now, use the central subdivision, Mumford degeneration of it, to break it up into several reducible pieces, put a log structure on it in the previous fashion. Now the log structure is singular locally in exactly the way that we just treated. So locally we can produce smoothings. And now it's just a matter of gluing these local smoothings together. Okay? When you have two smoothings, you consider an overlap between open patches, the two smoothings on the overlap, they actually glue because of the uniqueness that we just proved. Okay, so the smoothings are unique, so you can glue them on overlaps, but the tricky part is to prove a co-sample condition. And there's been technology around to prove it in the Bogomolov-Tian-Todorov theory. And the key ingredient for that is the degeneration of the Hodge-Ruddat spectral sequence. Okay, so that's the main thing that you need to show in order to get the smoothing once you have it, smoothing is done. So the setup is we have a toroidal crossing, and proper Fano X. So for instance, you start with a toric Fano variety and you break it up by Mumford degeneration into reducible pieces. And together with a log singular structure. Log singular. Log structure. And that one that permits, that's the assumption, that permits local log smooth resolution. Just as before in the affine case. Now the key ingredient to produce smoothing, as I said, is the Hodge-Todorov degeneration. We have to show that this spectral sequence, once more, it's looking very similar to what we had already, but now it's global, so the X is compact, and no longer with the compactifying divisor, but so the space was already compact to start with. Okay, so this needs to degenerate. N1. And for that to happen, we can apply a nice theorem. Okay, so once you have that degeneration, you can then apply a smoothing machine by Bogomolov-Tian-Todorov, Chan-Loma, adapt that to the log setting. I mentioned it in my talk in the morning. And then you get smoothing of X. Okay, so that's what happens. In order to have this log Hodge-Todorov degeneration, you use a theorem by Felten. Okay, so Felten here, in his thesis, 2019, he proved that 3 ingredients are enough for the spectral sequence to degenerate at N1, which is all we need. The 3 ingredients are coming here now. So it's base change, existence of local Frobenius liftings, and the Cartier isomorphism. If you have these 3 things, you get the degeneration. So the last part of my talk, I'd like to explain that. It's quite a general method. And if you know how Deline and Lucy proved the degeneration of the Hodge-Todorov spectral sequence in the classical case for smooth varieties, they use spreading out into finite characteristic, and then they use what's called the Cartier isomorphism. So it's generally something you might be interested in knowing. You can learn it a little bit now. But I'm also in particular talking about the log setting, where things are, have their special perks. It's not quite directly working as they prove it. You have to take care of some special things that would not happen in the ordinary setting. What is the base change? Base change means the base change of the sheaves of differentials. So that are these sheaves WPX. Let me explain what's meant by this particular diagram along which you wanted base change. You start with your toroidal crossing space X. Okay, so for instance, you can think of something that has 2 components. For instance, it's a reducible space, has a single log structure. And the first step is to spread it out over a ring, which is a finite extension of the integers. Okay. So the field C, so I should put spec here everywhere. Remove that here, put your spec. So whenever I put a field in the base, I mean spec. There's a general procedure how you can do the spreading out. Okay, just put it here. Spreading out means if you have a variety over a field of characteristic 0, you want to identify the variety as a generic point, as a generic fiber of a family of varieties over an integral extension of Z. So R is finite over Z. It's a ring that's finite over the integers. For instance, you take the integers and you remove some primes, localize. Well, that's not finite. Well, but that's also fine. You can also do that. Maybe it's not necessarily finite. So you consider, you make your original variety be the generic fiber of a family where you have a ring finite. That's like a Ganzheitsring. That can be done with almost everything, so that's not a difficult step. You can spread this out. And then once you have done that, you can go to the primes that are part of R. And so you have these finite fields sitting around here now. FP. There are points in there, and you can look at your variety over finite fields. And so these are all Cartesian diagrams. In other words, your original variety now becomes a variety of finite fields. And in order to make any relationship between them, you want to compare the differential forms between them. And that means you need to have
It
some
probably means
base change statements.
finite fields, not FP. FP to the R. FQ.
Yeah, you're right. I'm a bit, yeah, you're right. I hope just by laziness, I would omit this R. What's come. Yeah, thanks, that's right. So the statement that we want is that we have some base change of sheaves, which is just saying that the natural map where you take the pullback of your differential forms on XR, there's an injunction map going into the forms on the FP guy, or FP to that's an isomorphism. It needs to be an isomorphism. So ordinarily, if you were working with ordinary differential forms, that would always be an isomorphism. Okay, that's not an issue normally. But since we define our differential forms as a push forward from the log-smooth locus, we might have an issue here. Okay, so this is an issue. His statement is like a commuting of push forward and tensor product. Commuting of tensor product and push forward. Okay, so that doesn't commute in general. And in this particular case, we're commuting. So that's equivalent to saying that this adjunction map is an isomorphism. So that's something we need. Okay, so it's an ingredient we need to even make sense of it, to tackle the proof of Hodge-Todorov regeneration. Okay. So the next thing that we want is that we have local Frobenius liftings. Okay, let me introduce you to the Frobenius diagram, which you may have seen before. So we now have this variety over the finite field, and Miles is right. It's generally not FP, but FP to the R. But I'm lazy as I said. So just think of it as FP. And on that variety, you have two types of Frobenius maps. You have a Frobenius downstairs. Frobenius, remember, is just taking Pth power. So in the field FP, you can take Pth power. And that's a Frobenius morphism. And you can pull back the original variety along this Frobenius map in the base. Okay. Again, I'm omitting spec of the field downstairs, just put the field there. But then also the variety upstairs does have a Frobenius, by taking p powers of functions. That's the Frobenius upstairs, call that Frobenius of x. And taking these together, you also have the map here downstairs. That's the original map. You get an induced map from the Cartesian property that we call F, and that's called the relative Frobenius. Okay. It's a general construction that happens a lot, and it's called the relative Frobenius. Okay. And this diagram exists, no problem with it, but you might want that diagram also on a base space that's a little bigger than FP, and that's called the ring of second width vectors. Okay, so locally on X, oops, locally on X, this diagram needs to exist also over what's called W2 of FP. Okay, it's a ring of second bit vectors. It's like a first order deformation of FP, roughly speaking. And you want that diagram in exist over this ring in place of the field FP. Okay, so you want a similar diagram where in the base you put this ring of second bit vectors, and of course there's always stuff upstairs above it also. And in this case now, this relative Frobenius map does not necessarily exist. Okay, so you want a relative Frobenius also with this first order thickening bit vector ring. That's an extra feature you need to have. Okay, that's something it's called the existence of local Frobenius liftings. Frobenius lifting in the sense of lifting to the ring of second bit vectors. That lifting is being used to construct what's called the Cartier isomorphism. That's the third point in the strategy of how you generally prove a Hodge-Duran determination. There's a natural map. It's called C for Cartier map. That's taking the mth cohomology of the push forward of the sheaf of differential forms, the entire complex, okay, and it takes the nth cohomology. So look in the diagram here. No longer forget about the thickening for now. We're not talking about bit vectors anymore. We use exactly this diagram that's written, and we push forward the differential forms along the relative Frobenius map. Okay, that's what happens here. And it's still complex, and then we take the mth cohomology. And there's a map from that mth cohomology group into the usual differential forms, but now on the space changed space. You see it here, x prime. Okay, that's what I mean by FP. Should put FP everywhere. And in order to construct that map, you use the existence of this local Frobenius lifting. Okay, it's part of the construction of the map. I won't go into too much of detail, but that's something we need, and we want this map to be an isomorphism. And Illusi already proved it's an isomorphism log smooth locus. Okay, because we know that already. We only need that it's an isomorphism also on the log singular locus. So the map needs to be, I should say that this map needs to be an isomorphism. An isomorphism. And equivalently, by what Illusi and people already proved, we need enough to show that the left-hand side upstairs is Z closed. What does that mean? So Z is the log singular locus. Okay, that's where stuff is bad. That's over which we push forward the sheaf differential forms, and that's why it's called W in Omega, because we pushed it forward. And Z closed means if you have a sheaf, she is Z closed. If the following is an isomorphism, you have the adjunction map to, you strict the sheaf to the complement of that locus, and then you push it back forward. Okay, so Z, J is the inclusion of X minus Z into X. Okay, so you call the sheaf Z closed if this natural map is an isomorphism, okay? Meaning that there doesn't really happen anything along Z. So we need to show this for the left-hand side, which is the cohomology of this push-forward theorem complex by the Frobenius map. Okay, sounds rather complicated. But that's enough. So once we have these three ingredients, you know that the Hodge-de-Graham spectral sequence degenerates, right? By general machinery, by the proof of the linear Z essentially. So let me finish my talk with telling you how you can actually get those three ingredients. First, the base change. So if you have paid attention in what I just did in step 4, where I produced from the compactification isomorphism of the cohomology groups, I produced the isomorphism in the affine situation. So decompactify the situation. That same works to prove the base change of differentials. So as for the base change, we use a Czech argument. Like in step 4. Okay, so it's again, you know, upstairs in the log-smooth situation, you have a base change. You just need to show it downstairs. And there's only then one term in the Czech complex where things might be different, but you know what's happening on cohomology. So the key step is here that you know that C star XR M to FP XFP. You might not know it for all primes, but it's enough to have it for infinitely many. Is an isomorphism for infinitely many primes. And you can deduce that from knowing that the push forward from upstairs is an isomorphism for infinitely many primes. Because that's true in characteristic 0, we proved it before. So the statement, you know, that if you take the differentials upstairs in the resolution and you push them down, that those are the differentials downstairs, okay? We proved that in characteristic 0, but because it's true in characteristic 0, it has to be true for infinite many primes. Okay, so you take those infinite many primes where it's true, and then you deduce for those primes by knowing that this also is true. Okay, that's how we prove the base change. That's fine. So we have the base change for infinitely many primes. This diagram works. Then the next step, we need the local Frobenius liftings, okay? Similar situation again, you want to push down from upstairs. So we use the existence of Frobenius liftings upstairs. Use existence of local Frobenius liftings. On the log-smooth space, okay? So all these statements are local, as you see. I'm working with local situations. Locally, we have a resolution, it's log-smooth. On log-smooth spaces, locally there exist Frobenius liftings. Can we glue those local liftings upstairs in order to have a global lifting on the space X tilde in order to then push it downstairs? And the answer is yes, because the obstruction gluing the Frobenius lifting upstairs lies in the group that we really control. Obstruction is in the first cohomology group of X tilde with the derivations. Okay, kind of nice. So, and we know that's 0 because that group 0, we have no obstructions in gluing on X tilde the local Frobenius liftings, and therefore we have a global Frobenius lifting on X tilde. Then we can take global sections, and that pushes it down to get a Frobenius lifting. Frobenius lifting on X. Okay, so that point's done. Final point, the Cartier isomorphism. For that, consider this diagram where we now, it's the same diagram as here, the Frobenius diagram, but now put the resolution into play. So imagine, again, the situation is just local. The only argument, Cartier isomorphism is a local argument. So just do this, you know, add the resolution into the play. And we know that we have a Frobenius, the Cartier isomorphism upstairs, and you basically want to push it down. Okay, so I'll tell you how this works. So the equivalent statement was that we need to show that the left-hand side here is Z closed. That's what I'm going to prove now for you. So HM of the push forward of the differentials, that needs to be Z closed. That's the same as pushing it forward from upstairs. Okay, so put here F star pi star WX tilde. Oops. So I want to make a statement for this part down here. So I push forward along this map, the differential forms, and then take a cohomology of that, okay? But that's the same, I know that I can push it from here, okay? I just used that already before, that the differential forms push down from upstairs for my infinitely many primes, and work with one of those infinitely many primes where this works. So I push it up from downstairs, and then I use the commutativity of this diagram, which means that I can do this. It's the same as the M's cohomology of first pushing down, or first taking push forward Frobenius, but now Frobenius on the log smooth guy of the forms upstairs. Okay. Now, in the next step is I want to commute the push forward with taking cohomology. Why does that work? Okay, so I claim that's the same as commuting with taking cohomology. And that was true because the higher derived images of the push forward are vanishing for k greater to 0. Okay. Again, similar argument as we have used before. So that then allows us to use the Frobenius, the Cartier isomorphism upstairs, which identifies the sheaf with the differential forms on the Frobenius base change space by Cartier isomorphism upstairs. ISO upstairs. And now, finally, we use once more that the push down of the sheaf upstairs is the sheaf downstairs. Okay, so this is now the M prime downstairs. But this one is Z closed. Okay, is Z closed by construction by definition. Hence, this sheaf is Z closed, which we started with, and that was needed to be shown to know that this is a Cartier isomorphism. So the upshot is we're done and get a smoothing of X of the